So the F0 unit is here within the membrane, and it kind of looks like a ring, okay? We are going to focus in on kind of two parts, the C ring and the A subunit. The C ring is connected to the gamma subunit of F1, and at this point it's important for us to note that when the C ring rotates, the gamma also rotates. But why and how does the C ring rotate? So here we have a more in-depth cartoon, folks, where you can see that the C ring is rotating. The gamma subunit is also rotating. However, the A subunit is stationary within the membrane. What's going on really comes down to what is happening with all of those C subunits that make up the C ring. It is thought that there is aspartate, an aspartate 61, that is important for the translocation of protons. Now, of course, when aspartate becomes protonated, it goes from being negatively charged to being neutrally charged, right? And it is thought that this charge results in a conformational change that leads to the rotation. So a protonation event here changes the charge at this location and causes a shape change. Let's dive into those details. So, all of these circles down here in the C ring represent the aspartate. It is thought that this aspartate in the C subunit is attracted to an arginine in the A subunit. Since aspartate is negatively charged, it's kind of pulled towards that positively charged arginine. And once that aspartate is protonated, it becomes neutrally charged. And so it is no longer attracted to the arginine, but the next negatively charged aspartate is, and so forth. Let's draw out what I mean by this, folks. So here's the A subunit with the positively charged arginine. Let's draw in our C subunits. And I'm going to simplify this a bit, folks. So these are all C subunits. And they each have aspartates. And that aspartate is negatively charged. Coulomb's law tells us that there should be an attractive force between the negatively charged aspartate and the positively charged arginine, which causes the aspartate to rotate towards the arginine. Now, as this rotation happens, protons come in and bind to the aspartate. What's happening, folks, is the C ring becomes kind of exposed to the higher concentration of protons in the inner membrane space. With a lower pH, the aspartate would tend to become protonated due to its pKa. So, with a more with an increased concentration of protons in the inner membrane space, once the C subunit is kind of exposed to that, it'll suck up a proton and bind, becoming neutrally charged. So then, this aspartate here, folks, is no longer negative, so it is not attracted anymore to the arginine. Rather, the next aspartate in line is negative and kind of rotates again towards the arginine, and as the rotation completes, that proton, another one, is picked up. And as we rotate around the C ring, eventually we end up with a part of a C ring that is exposed now not to the inner membrane space, but to the matrix. And the matrix is deficient of protons, right? So it has a more basic pH. And so at a more basic pH, aspartate would tend to be deprotonated. So what happens is that proton is lost, aspartate becomes negatively charged again, and we start this cycle of negatively charged aspartates being pulled towards and attracted to this positively charged arginine in the A subunit, causing a rotation, which eventually results in a proton being picked up. Rotation continues, and eventually the proton is lost. So this is how we have protons falling down their gradient, and also causing this mechanical motion of the C subunit to rotate. Up next, folks, let's talk about the F1 unit.